So the individual round is just like the last year. There will be a set of problems which you will be working on. So it's quite simple as that. And then round 3 will be the team round, which will be followed up after that. So it's a team round, okay? So round 1 starts next week. To participate in it, make sure to send your topic of research by tomorrow by email to helpdesk@cheenta.com. Okay. Okay. So I'll just start recording. Yeah, of course. Yeah, the recording is also there. Okay, so now that's done. Now let's go ahead and talk about today's session. Now, what I plan to do in today's session is the following. I want to go over some of the problems that came up in the last year's last Winter Bose Olympiad, some of the problems that came up there, and it will give you an idea about what kind of problems you might face this time. And we will be discussing some problems related to that. So let's start with the easiest one. Suppose x cube plus y cube is given to be equal to 3xy minus 1. So it's maybe I can write it a little bit better. X cube plus y cube is equal to 3xy minus 1. This is given. Find x comma y. Find the number of pairs x comma y which satisfies this equation. So all of you give it a try. Find the number of pairs x comma y which satisfies this equation. How many such pairs of numbers x comma y will satisfy this equation x cube plus y cube equal to 3xy minus 1? Think a little bit, everyone. If you think you have an answer, do not tell the answer yet. Wait a little bit. Let your friends try, but you can raise your hand if you think you have the answer. That's fine. You can raise your hand if you think you have the answer. Okay, so I'll give you a yes, you can search up the internet, Aryan. That's fine. That's okay. But don't do it now. Do it after the session. So there is a very simple factorization which is quite useful. It is x cube plus y cube plus z cube minus 3xyz. Do you know how to factorize this thing? Any of you? Do you know how to factorize x cube plus y cube plus z cube minus 3xyz? How do you factorize this? Okay, so I see raised hand. Okay, go ahead, Aryan. Or Parth also is here. Yeah.
That's x plus y plus z into x square plus y square plus z square minus xy minus yz minus xz.
Okay. Minus xy minus yz minus zx. So somehow this product is related. This factorization is related to this one. Can anyone tell me how it is related? Okay, so we are getting some raised hand again. Let me go to Parth Vartak. Go ahead, Parth.
You can set z is equal to 1 and then you can move it up.
Z is equal to 1. Let's plug in Z is equal to 1. So if Z is equal to 1, then would this work? Yeah, this might work. So we will get x is x cube plus y cube plus 1 minus 3xy is equal to x plus y plus z. Sorry, this is 1. Right. So let's plug in plus 1 times x square plus y square plus 1 minus xy minus y minus z. This is this is the thing that we have.
So minus f.
So this is 1 again, sorry. So these two ones cancel off. So we have, sorry?
So if only minus 1 f will be minus f.
Okay, so just a second. This is minus xy minus y minus x, right? Okay, so what do we have? So we are given, if we bring this thing to the other side, we have x cube plus y cube minus 3xy plus 1 equal to 0. So this thing is given to be equal to 0, which means this side is also equal to 0, right? So if this is 0, then what can we say? We can say that x plus y plus 1 times x square plus y square minus xy minus x minus y minus 1 equal to 0. Okay, so we are very near to the solution. How would we solve it now?
So the second equation is true only when x is equal to y is equal to 1. So, sorry, the second bracket is 0 only when x is 5.
Okay, so what do we have? Either x plus y plus 1 is 0, or x square plus y square minus xy minus x minus y minus 1 is 0. Oh, sorry. Is it a plus 1? Plus 1. Yeah, plus 1 is 0. Okay, so now the question is, when is the second one equal to 0?
Then x is y is 1.
Okay, so you were suggesting then x is equal to y equals to 1. That means 1 plus 1 minus 1 minus 1 minus 1 plus 1. That is 0, definitely. That works. But is that the only value where it works? Or are there other values?
We multiply equation by 2. X minus y square plus y minus 1 square plus x
Ah, excellent. Very nice. So if you multiply this by 2, both sides, you will get x square minus 2x plus 1 plus y square minus 2y plus 1 plus x square minus 2xy plus y square equal to 0. So this is the classic situation where sum of three square numbers is 0. So if sum of three squares is 0, that can only happen when each of them is 0. That means x equals to 1, y equals to 1, and x is equals to y. That's the only case when this can become 0. Outstanding. So then the only case where this is 0 is 1 comma 1, which means that's the only situation when this is the case where this product becomes 0. Okay, what about this part? X plus y plus 1 equal to 0. What can you say about that?
So then let's just write it minus one. So that will have the minus.
So x plus y equals to minus 1. So that will again have infinitely many solutions. So what can we say about the number of equations, number of solutions to this equation? There would be infinitely many solutions to this equation. Is that the answer? Okay. So, for example, x plus y equals to minus 1 means you could have 2 comma negative 3 here, right? So if you plug in 2 comma negative 3, you'll get 2 cube plus negative 3 cube equal to 3 times 2 times negative 3 minus 1. So you'll have 8 minus 27 is equal to negative 19, which is true, obviously, right? So you can create infinitely many solutions like this on the for the first from the first parentheses. Okay, that's awesome. We got actually two different things from this particular problem. The sum of the square strategy, which is a very powerful strategy in mathematics. If you have a collection of pairs, a collection of squares adding up to 0, then certainly you can say each of them are 0 individually. This is a standard strategy to solve problems. Okay, so this one is done. Let's go to the next problem. And this next problem is the following, that there is a triple of sets. So there are A, B, C. There are 3 sets, comma, comma, bracket. Okay, so basically it's an ordered triple of sets. Each of them are sets such that A union B union C is the numbers from 1 to up to 2003. And it's also given that A intersection B intersection C is phi. So A union B union C is the set 1, 2, 3, 4 up to 2003, and the intersection is phi. It's empty. The intersection is empty. Now the question is this. The question, what is the value of, so how many such triples are there? How many such ordered triples are there? Give it a try, all of you. How many such ordered triples are there?
Sir, ordered means we don't have to count the permutations, right?
Right. For example, if 1 comma 2 is a set, 3 is another set, and 4, 5 up to 2003 is another set, then you have to count the permutations actually. So you basically, so this is a different set. So 4, 5, 2003, 3, 1, 2. You have to count this separately. Yeah. So how would you go about proving or finding out such triples? This counting process can be really interesting. It's not given that the entirety of these things are disjoint. So they're not pairwise disjoint, that's not given. But they're altogether disjoint. So nothing is common in all three of them. Yes, go ahead. So we have Aryan Prakash raising hand, but I'll wait a little bit, Aryan. You have a question or you want to give us a solution?
So not exactly a solution, an idea. I got an answer with that, but
Yeah,
I'm not sure, sir.
okay, go ahead.
So, sir, the idea that I used is first we can take the total number of, like, if there are no conditions, only A union B union C is 1 dot 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 till 2003. The number of such triples is 3 to the power 2003, because
Number of such
A has
triples is 3 to the power 2003. Okay. So let's see why he's saying that.
oh, sorry, it's wrong. It's wrong. I just realized it's wrong.
Okay, okay, okay.
So I was thinking then we can subtract like the total number of cases from, if there is one element or maybe two elements or maybe all elements common in ABC, from the total number of cases, and that will give us the required triplets.
Okay. Okay. Tech toppers is having the same strategy. So, or both of them are saying that in total, if I may make some space here. So, if you want A, B, and C, and if you have 1, 2, 3 up to 2003, so you have to assume that they are like non-empty, I guess. Yeah, I think non-empty is fair to assume, but it's not given it's non-empty actually. But anyway, assuming that it's non-empty. Oh, 6 to the power 2003. Why is that, Aditya Vardhan? Okay. So he's saying not only ABC, include A intersection B, B intersection C, C intersection A. There are 6 objects, 6 elements. Okay. So why do you think it's 6 to the power 2003? Well, because you're saying that, okay, so you're suggesting that each element has a choice to go to the first one, to the second one, to the third one, to the fourth one, fifth one, sixth one. Is that right? Maybe you are saying that.
So, but then, if like number one goes in A, it doesn't seem which then it will happen to in A and B both. So how will it be?
So, yeah, so you have to be very careful here. What we need to do is we will be this will work. What Aditya Vardhan is saying is going to work, but we have to really understand what's going on. So let's draw the Venn diagram. There are how many regions? There is 1, 2, 3, 4, 5, 6. There are 6 regions in this picture, right? If this is A, if this is B, if this is C, this part is empty, the A intersection B part. So nothing goes in there. Now, if we remove that part, we have precisely 6 distinct regions where each element can go, right? So instead of A, I should write 1. which would signify the region 1. Region 1 is this, that goes exclusively to A and nothing else, right? Similarly, we have 2, which is B. We have 3, which is C. So I can write exclusively to A, exclusively to B, exclusively to C. Okay, and then A intersection B and not C. So you have to be very careful. So it's not A intersection B. It is A intersection B, not C. So that is this number 6, number 2 in this picture. This is in golden maybe. A intersection B, not C. So this is golden. And then we have this A intersection C, not B, B intersection C, not A. So this is 2, this is 6, this is 4, and this is 6. So we have 6 regions. It's a very interesting problem. You have 6 regions, and each number can go to exactly one of the 6 regions. Is that acceptable to all of you? Do all of you understand what I'm saying? Each number can go exactly to one of the 6 regions. So for 2000, and it must go to somewhere, right? It must go somewhere. So it is 6 to the power 2003 choices in total. Okay, does that completely solve our problem?
So,
Yeah.
so let's just some element is in intersection B, then it has to be in both A and B. What about that?
You see, Bart, what I just said? It's not A intersection B. It is okay, so that's true. So this is not A. This is exclusively to A. There's a difference. I'm not taking this entire A. I'm taking this region as my region 1. Do you see what I'm saying? Okay.
Yes.
So now we have 6 options, 6 places where this can go. So 6 raised to 2003 is the total number of cases that we can have. Okay, so if that happens, is that the answer? Okay, so Aryan Prakash is saying the answer should be 2 times 6 raised to 2003 minus 7 raised to 2003. Why is that?
So I think because 6 to the power 2003 are the total number of cases, and we have to subtract those in which A intersection B intersection C is not 5, meaning there is something common. Either one element is common, and that can be the number of ways for that is 2003 C1 times 6 to the power 2002, or there are 2 elements in common, and just one till 10 elements are common.
So how can
And then we test it.
but the question is, how can the elements be in common? Because the way we have
So we
selected it,
and then we subtract them from the total cases.
so I'm saying the way we have stipulated this picture, nothing is going in here, right? Nothing goes here. So if nothing goes here, we do not have to subtract that case. So maybe something you have to think a little bit more.
Yes, sir.
So think. Because when we are sending objects to, remember, we are not sending to A, sending to B, sending to C. We're not doing that. What we are doing is precisely not that. We are doing exclusively to A, or exclusively to A intersection B, not C, something like this. So we have precisely split up the regions into 6 regions or 7 regions, so to say, and nothing goes into the first region actually. Okay. Okay, so Shauradip is thinking that it is 6 raised to 2003. Okay, so no other condition is given. Okay, so I gave you the strategy. You have to sort of convince yourself if the answer that you're getting is correct or not. But the general strategy, this is true. If you have, so if I can stretch this a little bit more, what if I have, what if I have 4 such sets? So if I have 4 such sets, suppose 1, 2, 3, and if I want to draw another one, I'll be in big trouble. But maybe there is one that cuts through all of them, like this. So can you guys draw a Venn diagram with 4 blobs? Venn diagram with 4 blobs. How would that even look like? And how many regions do you think it is going to have? It's a good question, actually. You can think about that. In fact, let's think about that. Let's think about how many blobs will be there, how many regions will be there, how many regions will be there in a Venn diagram with 4 blobs. Let's remove this. How many regions are there in a Venn diagram with 4 blobs? Okay, so we are getting some answers. Parth is raising the hand. Okay, Parth, go ahead.
So I don't have a update solution. I just have an idea.
Okay.
So there's only one circle, and only one set, then there's only one root. When there are 2 sets, there are 3 regions.
Okay, let's even make it easier. When there is one circle, there are 2 regions, like one inside and one outside, right?
Yes, sir.
So let's make it like that. Okay, so let's say 3 regions.
So then for 2, there will be 4 for 8. So it will be 2 raised to n.
So Parth is saying that it's 2 raised to n. But even if we go for third one, something weird happens here. So this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So for 3, we have 7.
So we have 8, right?
So one, two, three. Oh, sorry. One, two, three, four, five, six, seven, eight. Correct, eight. So let's do it for four. We will see it's not actually 2 to the power n, but anyway, we will see that. So can you give me the fourth one, Aryan? Yes, Aryan, go ahead.
So I think it should be, if you're counting the outside, and yes, I think then it should be 16. Because there will be 4C0 plus 4C1 plus 4C2 till 4C4.
Okay, so okay, maybe we can explore this a little. Sorry,
So can you wait for 1 minute?
can you what? Sorry,
So can you wait for 1 minute?
can you wait for 1 minute? Yeah, sure. So we have the third one, and then we would obviously need another one for the fourth one. So the fourth one will be somewhat like this. This is a very interesting problem. There is a book called Brualdi on combinatorics. You guys can check that out. It's a very beautiful book. That has, I remember that it has this problem in that book. It's actually a very famous problem. It's a very separate problem actually. What you get for n such circles. So why I remembered this, I'll tell you why I remembered this problem. This is a counter example of the guesswork system. So in Olympiad mathematics, in fact, in any mathematics, um, you tend to see a pattern and you sort of quickly want to guess what's going on. And if you do that for here up to 3 cases, it seems it's 2 to the power n. If I'm not too wrong, I might be wrong actually, but if I'm not too wrong, I think the fourth one will be 14. But let's check. Because this, if I'm correctly remembering this is probably that problem. Maybe not, maybe yes. Let's check. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yep, exactly 14. Seems like it's that problem. Oh, what? It's not the right diagram. So A, B, C, D. Why can't I do A intersection D? It's here. This is the A intersection D.
So the counter example.
You see, B intersection D is not possible. B intersection D is possible. It's this one. This is B intersection D. Okay, I see what you're saying. Okay, B intersection D is this entire thing. So what you are saying is B intersection D but intersect nothing else is not possible. Is that what you're saying? I think Shoradip is saying is that this picture has this weird thing going on, and that's correct actually. You see how what Shoradip just observed, and it's a very good thing that he observed. In this picture, we don't have a region which represents B intersection D and B intersects nothing else. So really to make it, and the same issue is with A and C. So to make that happen, what you have to do is sort of artificially move these two things and make them intersect each other. And the same thing is true for this red one. So you got to artificially move this red one sort of beneath this and go and sort of intersect with B. So this region is B intersection D and nothing else. and this region is A intersection C and nothing else. Very nice, Shorodip. Excellent observation. We have peculiar knot-like figures to actually make it happen. Okay, so as a homework, you guys can of course work on a general formula. So this is the weird picture. We don't want this weird picture in general. What we do want is find a formula, find a formula for number of regions when n circles intersect and no three are concurrent and no three are concurrent. So when n circles pairwise intersect, so each circle is intersecting the other one non-tangentially, okay? And is a counter example to the guessing algorithm in some sense. So what do I mean by that? What I mean is you see a pattern of numbers and you start guessing. Okay, this might work, this might work, this might work, this might work. For 1, it's 2. For 2, it's 4. For 3, it's 8. Boom, you have an idea. You say that, okay, maybe for 4, it's 16. For 5, it's 32 and so on. No, that doesn't work always. Maybe for the first 3 things it works. But for 4th onward, this doesn't work. It's a very beautiful problem. It's a counter example to that particular thought process. So I do have to stop out here today as we are out of time, but we will continue next week. In the meantime, please send me your research project topic to helpdesk@cheenta.com. You can email it there and then I will respond to that. Okay.
So, to send the email first of the topic only, or
First the topic, please, by tomorrow. Once the topic is sent, we will be responding with a answer that okay, this is okay, you can go ahead with that and so on. So then you can do the PPT and send it by next. Yeah, so some example topics are Pell's equation is an example. Another example is projective geometry. Another example is Steiner deltoid. I mean, these are some of the cool things that I can remember over the top of my head, but you can obviously find out more. There are many beautiful ideas in mathematics. You can, yeah, sure. Shorodip you can do that. Make sure it's serious. Make sure it shows that you have actually researched the matter and tried to get a result. Try to get a good understanding of what's going on. Don't make a very large presentation. Make at most 7 slides. Yes, Parth, go ahead.
so can we like use the help of the lab to
And send your name, a display picture, because we'll make you a poster in your name so that you can invite maybe your friends. It will be a YouTube live, so you can invite your friends maybe. So name, display picture, and a little bio so that we can PPT by Wednesday night, right? Yes. Also send this. Okay. Yeah. Sorry, Parth, go ahead.
so can we use search on the net for the
Yeah. Yeah, you can do that. Certainly. You have to use internet, but make sure to use good resources. A very nice resource is Cut the Knot, a very beautiful website where there are many beautiful ideas in mathematics, pre-college level mathematics. So you can definitely use that. Okay. All right, guys. Thank you. Bye. Take care.